I would like to introduce Dr. Rolf Schlake, Chief Technical Officer of ASR USA, to present what is supercritical fluid.
Okay, thank you very much. Is everyone in now? Okay.
Yeah.
First of all, I would like to thank you very, very much for the invitation to come here. First of all, Dr. Sahan from Future University, thank you very much for the opportunity to come to talk to you as well. Dr. Salama, thank you very much as well. And all the people from MAPATCO, Dr. Mukfa, thank you very much for this invitation to have an opportunity to speak with you all. I have a lot to talk about today, really a considerable amount. And if I do not finish, I want to make sure this works here. There we go. There we go. Now, I would like to also special thanks for Mohammed Halmi. I'd like to say thank you very much for Mohammed for inviting me here to come here as well. Now, Mohammed has come to our facility in the U.S., and any questions that you may have that I'm not here, he has learned everything. So come and ask him. He will be aware of everything. You can just direct all the questions to him. What I'd like to do is talk a little bit about overview of what supercritical fluids are, and what a little bit about the history, where we use them, and some of the examples that I will be using. These are all from applied separations. There are many, many different kinds of applications, and I would really just give you an overview of many different ways that ones can use supercritical fluids. After that, we'll have a little bit of a break, and then I'll talk about the various applications. I will be very quick. Now, Mohammed tells me that since I am here, I'm an American, and I must speak more slowly. Okay? However, if there's any time that you have a question you do not understand, please raise your hand. Please let me know immediately. And if I talk too quickly, then tell me to speak slower. So, okay, we will talk about, and I have so much to cover here, so much, that more than likely we will not get through it all, but I will go through some of it exceedingly fast. I give this course many times to the ACS, American Chemical Society, short courses, and this can be a one-day course or it can be a two-day course. Naturally, I will not cover everything, but there are some areas here that I will not be able to cover, but I want to introduce them to you, so you'll understand the many different ways that we can go ahead and work with supercritical fluids. After the break, I will talk about nanoparticles, talk about natural products and general processing, essential oils, how we can separate essential oils. We'll talk about seed oils, and we'll talk about nutraceuticals, and then I'd also like to introduce you to the idea that we can do extractions of liquids also with supercritical carbon dioxide. And primarily this is done with countercurrent, although I will touch upon an anti-solvent mechanism. That being said, one of the things that I get asked all the time, and excuse me, but I have great difficulty standing behind the podium. So I'm going to move back and forth, walk around. If I get in the way, say move. Okay, supercritical fluids. Where do I use them? Where can they be used? Can be used everywhere. It's like water. I can make tea with water, or I can make electricity with water. So many different ways that I can do things with supercritical fluids. Again, we will only touch upon some very few ways. Some of the examples, now what I would like to do, even though I come from applied separations and we make the equipment, I will give you only a very short commercial. We make equipment from laboratory scale, very small scale, to 1,000-liter pressure vessels. Very large production that we can manufacture. The pilot scale that is at Mapatco is a 20-liter system, a single 20-liter vessel. This is a smaller pilot system that is very, very useful for scaling up to larger systems. That being said, why are we interested in supercritical fluids? There's a great deal of interest that has occurred lately over supercritical fluids. Because it's the health and the environment. It really is going green. This is the major push behind this. It's the environment. That means we do realize global, despite the fact that the current president of the U.S. may deny it, there is global warming. VOCs, volatile organic, water shortages, the disposal hazards of hazardous solvents, and everyone now is concerned more and more with safe food, organic foods, and the idea of no residues in the food, making this more and more a halal type of food. And then in addition, we're also looking for better health and environment for our workers. Other reason for supercritical fluids outside of this is the area of nanotechnology. If we're dealing with the very small, we have to also deal with new techniques. Areas that we could talk about would be electronics, material science, for example, aerogels, smaller particles, and the ability to get into small spaces, for example, medical implants, to clean these. All of these are being used, are applications for supercritical fluids. Natural products, we talked about this morning, and I will talk about this after the break. But here are many examples of the different areas where supercritical fluids are used. Natural products, foods and pharmaceuticals. These are some of the pieces, but I will use examples of our equipment here, but I don't want to go into it in any great detail. But I will use these as various examples that I give you. Whether we're talking about the decaffeination of coffee, or whether we're talking about something like defatting nuts, and I will talk about that a little bit more, some of the interesting techniques that one can use, even with doing things with tree nuts or even ground nuts, for example, peanuts as well. And then also, we were involved with the natural product Taxol. Taxol was developed by Bristol Myers Squibb on the equipment that we had from the extraction of the Pacific yew tree. It was then, this is the major drug that is used for breast cancer and ovarian cancer.
Please slowly because it's students.
Slower?
Yes.
Okay, sorry. Please tell me exactly. I can speak a lot faster. I'm trying to slow down. In addition, flavors, fragrances. To separate it. I'll give you a little bit of a talk on how to separate some essential oils. Now these are used by some of the major companies that are around the world. IFF, Givaudan, Firmenich. These all have our equipment to go ahead and do this sort of thing. We have a big effort right now in waterless textile dyeing. That is to put in fabric, goes in dry, it is dyed with supercritical CO2, and then it comes out perfectly dry. We have a big effort doing that right now. It seems rather unusual, but now instead of doing an extraction, and this is the important part of this, we are not doing an extraction, we are dissolving the dye in the supercritical fluid, and it is then being deposited in the textile. Completely, totally environmentally friendly. It uses no water. Now I want to give you another little bit of information. We were involved with a very unusual, small application. This had to do with dating the art here in Egypt. We were given an exceptionally small piece of art, and we had to go ahead and date this. We had to do a very finite extraction of a tiny sliver. We had to extract the propolis, and that propolis then was used to go ahead and date pharaonic art. It was apparently the work that we were given. This was when it was ultimately dated. It was something like, 3,000 years before the Common Era. So it was quite old, certainly by American standards. We've also been called in by the Smithsonian Institute in New York, in the US, to involve ourselves in the restoration of the Hunley. Now this was a submarine in the American Civil War that was sunk, and we had to bring it up. We didn't bring it up, but we were involved with the restoration of this archaeological finding using supercritical carbon dioxide. Big effort right now. Cleaning of medical implants. This is the way that we've done work for Johnson & Johnson, Synthes, DePuy, all have systems like this. What we have in the situation now is, you see, the old days when an implant, we say for a hip implant, for example, oops, go back. When you had a hip implant years ago, it was a solid piece of stainless steel. By using some of the physical properties of supercritical fluid, which we'll touch upon, we can now get into those small little spaces to actually clean. It would take hours to do this otherwise. Now it can be done in a much shorter period of time. Not only can we go ahead and clean, but we also take some of these parts of an implant. For example, the hip ball. We can infuse antimicrobials, anticoagulants into the plastic as well, into the polymer. And then this will ultimately migrate out, but winds up being a time-release mechanism to do some of this. So again, not only can we do extractions, but we can do infusions into a variety of polymers. And I'll talk a little bit more about some more of that. Material science. We've been involved a lot with the US space program, NASA, where we've gone ahead and used the physical properties of supercritical fluid, where we're drying aerogels. Aerogels are highly porous materials that provide great insulation for heat, great insulation for acoustics. So what we wind up doing here, as you can see by this right here, that small little piece is capable of giving this huge amount of insulation. Instead of having a meter, 2 meters thick, now we can use a very thin piece. And this is what's used in the space program currently. A couple of areas where our technology is being used. In addition, there are military applications. We've been involved with the US military in what we call obscurants. Instead of having the individual particles fall together agglomerate, with supercritical processing, you can keep these particles from agglomerating. They will then be dispersed and don't fall to Earth as quickly. We can also deal with different frequencies. We can deal with the IR in this case, so that we can now have, for example, taking a very finely divided flakes of aluminum, coating them, all this being done supercritically. Specially integrated circuits. And now here's an unusual one as well. I use the term loosely, laundering money, but this really means what we're doing here is, because of the many anti-counterfeiting measures that go on in currency these days, they are very expensive to print. So trying to extend the life of a banknote is one of the objectives here. And you just can't go ahead and take the banknote and put it into the washing machine and wash it, because now you will defeat all of those anti-counterfeiting measures. However, if you pick the right conditions, you can remove all the skin oils from the currency and still maintain the anti-counterfeiting measures. Again, this is a big savings for the individual governments that have done this. We've done this in the United States, and there's a trial going on right now in India. Nanoparticles. The inhalation, making small nanoparticles using, and I will talk a little bit about the methods in the second hour here, about how we can go ahead and do that. Making nanoparticles for pharmaceutical products, for example, inhalants, asthma drugs. We work very closely with Pfizer on the inhalation of insulin. This has not gone to market much, but what we have done is we work with Pfizer in using our equipment to do some of that work as well. Another application of infusion is to go ahead and you can actually put metals into the variety of different polymers, into carbon nanotubes. We did this work in conjunction with NASA, the National Institute of Aeronautics, and the Boeing airplane company, you know, Boeing. New environmentally friendly ways of making Nike shoes. We have a big program going on with Nike right now. We've also done some other secret work, which I can't tell too much about, obviously, but we've worked with the U.S. Air Force and the Defense Advanced Projects. This is the very highly secret part of the U.S. Defense Department, where we were beaming high-energy microwaves through a stream of supercritical CO2, and developed a system to go ahead and do that, because we were doing a high-energy reaction inside the reaction vessel. You can make anything supercritical. We do a lot of work, mostly in supercritical carbon dioxide, but water can be made supercritical. We can deal with supercritical propane, supercritical DME, dimethyl ether, fluoroforms, methanol, all of these can be made supercritical. We just have to pick the right conditions. Now, safety considerations are very important, obviously. When you have supercritical propane, it's not a good idea to smoke in the environment. I'll talk about this a little bit more. Liquid countercurrent, so you can extract liquids with supercritical carbon dioxide as well. So where do we start? Just like every morning, I start with coffee, and many other people start with coffee. Methylene chloride used to be used to decaffeinate coffee. Back in the 1970s, the German Ministry of Health said, you can no longer use coffee anymore. And the reason for this was that, too fast? Too fast?
Too fast, yes.
Too fast.
Too fast, yes. So please, again, slow.
Okay. Please tell me. That's good. That's great. Back in the 1970s, coffee was was decaffeinated using methylene chloride. Now, the problem was, and exactly as Dr. Mukhtar pointed out in his very good presentation, he talked about the residue in products. And this was the major impetus. There was a residue of methylene chloride in coffee, in the decaffeinated coffee. The German Ministry of Health said, you have to bring this level down more and more and more. And it wasn't that they were not able to do it. So if you couldn't use methylene chloride, what would be some of the alternatives? Benzene?
Oh my God. More ways.
I don't think so. DMSO? No. So neither of those are good possibilities. So I had to come up with a whole brand new idea, and this was supercritical carbon dioxide. These are some of the first large-scale ventures. So that being the case, if you can decaffeinate and use supercritical carbon dioxide to do tons of coffee, it is applicable to many, many, many different applications and many different scales of operation. Okay, what is a supercritical fluid? Now I know that many of you have worked with supercritical fluids, so but then some of you haven't. And I always find this to be a very difficult set of circumstances when I have to work with an audience where some of the people are extremely knowledgeable, then I should hand them the mic, and they give the presentation to others that can barely understand what supercritical fluid is. So usually what I try to do then is kind of go down in the middle of the road. So I will talk a little bit about both of these on both sides. I will try not to be too basic, but those of you that are well familiar with supercritical fluids maybe can use some of those ideas to explain to your boss that holds the budget, explain to him that is not a scientist, that he might understand the technology a little bit better. So use it for that purpose, perhaps. Let's say, where was this discovered? Well, it was really discovered back in the early 1800s by a Frenchman, the Baron de la Tour. And he was a really clever guy. What he wound up doing is taking a cannon. He put a cannonball in it, sealed it up with some ethanol. Why he picked ethanol really doesn't matter. But he wound up sealing this up, and then he heated this thing and rocked it back and forth. He rocked it back and forth by increasing the temperature. The pressure increased. There were two phases. As he rocked it back and forth, as the temperature increased and the pressure increased, he realized that the sound changed. Going from the dense liquid then to the gas, there was a difference in the sound. And as he increased the temperature more and more and increased the pressure, ultimately what he found was there was no change in the sound. So looking at this, we had a liquid and a gas here. Ultimately, by increasing the temperature and pressure, it became one phase. Ultimately became named as the supercritical fluid. But it became one phase after reaching a critical temperature and a critical pressure. Very quickly, we're all familiar with the chemistry of early gases. We have here Gay-Lussac's law. This is by increasing the mass. We know of all of these individuals. So I'm going to pass through these very quickly. Charles' law. Boyle's law. And then we throw in Avogadro. Now, we put these three together, This is called the combined gas law. And remember this from our very early chemistry days. We throw in Avogadro into this, and we have what's called the ideal gas law. And we're all familiar with PV equals nRT. This was grained into us, PV equals nRT. But now when I bring it up to a supercritical fluid, here is my response. Forget it. It doesn't work anymore. So, what is a supercritical fluid? The easiest thing to do is to go into a three-dimensional PVT surface, and I'm going to go ahead and take a part of that in a phase diagram. We've all gone through this, so now I am going to speak quickly, because everyone knows this. If we start with a liquid and we increase the temperature, then we increase the pressure. First of all, when we increase the temperature, it goes to a gas. Water goes to steam. We increase the pressure again, and it goes back to being a liquid. We seemingly could do this forever, but we can't. As we found out with de la Tour, as you increase the temperature and you increase the pressure, you reach this point where we have a single phase, the supercritical point. And we reach the supercritical point at the individual molecule, whichever compound we're dealing with, at its critical temperature and its critical pressure. Now, many times we also hear this term subcritical, a subcritical fluid. Just by definition, this is the area above the normal boiling point and below the supercritical point. And this really is not the English term fluid. It really still is a liquid. It behaves like a liquid, although some of the properties change a little bit, especially in water, subcritical water. For example, as you increase the temperature of the subcritical water, its dielectric decreases, so it becomes more and more non-polar. And this gives you some interesting ideas in a halal setting, for example. Now you can do extractions in water that are very similar to doing extractions with ethanol. Again, something for you to think about. And the equipment that uses supercritical carbon dioxide can also be used to do subcritical water work as well. Not supercritical, but subcritical. Really, what we have is, it's sometimes easy to explain this as a fourth state of matter, but really what we're looking at is a continuum. We start with a liquid, and around this we have a continuum of liquid gas. Oh, I did it again. There we go. It's not a gas, nor is it a liquid, but it has the advantages of both. We have the density to dissolve. But we also have these other characteristics: permeability, high diffusivity, low viscosity, no surface tension. And these are some of the properties that make it extremely valuable for many, many different applications. Now, what I would like to do here if you can see that, that's a video of something very exciting. Aren't you all excited? You're looking at supercritical carbon dioxide. Come on, this is exciting. I mean, for example, President Obama said, wow. And I think if you were to go ahead and show this video to President Sisi, he might say, no. Actually, I tell you, I was with President Obama, and I did ask him if he knew what a supercritical fluid was. And as a very good politician, he used the double meaning of supercritical fluid and said, I know that it's supercritical for you. Politicians. A supercritical fluid is somewhere between a gas and a liquid. And as I said earlier, we can make almost anything supercritical. For example, take a look at water. The conditions are different. And not that this is not found outside of nature, this is at nature. Supercritical water is in nature. It is at the bottom of the ocean, near the volcanoes at the bottom of the ocean. The water coming out of there is supercritical. Nitrogen. Think of it in the other direction. Look at those temperatures. Pretty cold. And actually, we have supercritical nitrogen in a scuba tank. Now, when it comes out of the scuba tank, obviously, it is at a gaseous state. But when it is in the tank, it is under the conditions of being supercritical. So it's not this unusual phenomenon that we're talking about here. It is a pretty common phenomenon that we have all over the place. There are many different areas where you can use supercritical fluids. Now, that is in this world, but then most of the time we use carbon dioxide. In this world, we're looking at not carbon dioxide so much, but if we move outside of the world and we go to Venus, we know that the atmosphere there is composed of carbon dioxide. However, if we go ahead and look at what the pressure is of the atmosphere, it's about 90 bar, 90 atmospheres, and it's 480 degrees, the epitome of the greenhouse effect. Now, if we plot that out, we see that that is supercritical. So the atmosphere really on Venus is supercritical carbon dioxide. Carbon dioxide is the most common one that we use. That's because it's safe and environmentally friendly. We recycle it, as we do in the pilot system here. We go ahead and depressurize, and then we boil it off. We bring it back to a liquid state, back into the storage vessel, and then it is reused again. We can do this over and over and over. Now, what happens often, however, is people that are not scientists think of carbon dioxide and go, whoa, this is a greenhouse gas. We want to stay away from carbon dioxide. But remember, we're not creating carbon dioxide, we are using existing carbon dioxide and then recycling it. It's inexpensive, readily available. As Dr. Mukhtar pointed out, solvents are very expensive. CO2 is much cheaper. How else can you make Coca-Cola? It's the same. The conditions with carbon dioxide are very mild. We saw that a minute ago that this is 31 bar, 74 bar, and 31 degrees. Very mild conditions. When you have a tank of CO2 in Cairo here in the summertime, it will be supercritical. As we pointed out with the coffee and the decaffeination, when we come back to ambient, there is no residue. Has zero surface tension. Well, take a look. Surface tension, 0, compared to the other solvents. This allows it to get into the small spaces. You're not held up at all. Gives you ability to move in and out faster. You can do these extractions because you are not now limited by surface tension. Tunable. And this is probably one of the most important considerations, especially in doing natural products extractions. We'll talk about tunable. Tunable, what does that mean? When we talk about tunable, very simply, we can talk about TV set, where we have one TV set, but we can go ahead and change the channels, and we have a variety of different programs. We tune the TV, tune the channels. Well, we can do the same thing with a supercritical fluid. In that supercritical fluid area, by increasing the pressure, we increase the density, thereby increasing solvating power, and we kind of simulate greater polarity. So we can go from a non-polar kind of condition all the way to a more and more polar. Now, I don't mean to say at all that you're going to make CO2 behave like methanol. That is not the case. I just merely put this in as a relative scale to show you that as you increase the density, you increase the solvating power. Let me give you another example. I give a lot of talks to non-scientists to try to explain the technology. One of the things that I use to explain phases is that if we were all in this room and we all now hugged each other very, very closely, we would be molecules that would make a solid. If we now dispersed, and there were only 3 or 4 of us in the room and we were in the far corners of the room, we would be very, very far apart from each other, and this would be like a gas. Now, if I throw a ball into the cluster of people, it's not going to be held there, it's going to not be dissolved. If I do the same thing with a gas and throw it into the middle, it's going to hit the floor, it will not be retained either, because the people, the molecules are too far apart. Now, if I, however, bring the molecules closer, if I increase the pressure such, now the molecules will become closer. Now van der Waals forces begin to take effect. These intermolecular forces begin to take more and more effect. We can now begin to hold hands. Holding hands all together here, we're very close together. And now we are a liquid. Throw the ball in the liquid, and now the ball will be held by all of us because we're holding hands and the ball won't fall down. So now we've understood what liquid, solid, and gas is. Now, let me now add another dimension to this. Let's make all of us move very, very quickly, but not move too far apart. If we're moving all very, very quickly, we're no longer holding hands. The van der Waals forces are not holding us together anymore. However, we're close enough. We are dense. Dense like a liquid. Now if we throw a ball, it will not fall. It will be retained. Now, we can extend this a little bit further. If we go ahead and say, we don't have hands, that's fixed if we're in a liquid. But if we're moving around now, we can move a little bit further out, still move around, so different size balls can be thrown. We now have the ability to go ahead and change the solvating power by changing the conditions, the distance away and how fast we move. So using this kind of analogy, you begin to understand what a supercritical fluid is. Liquids are nearly incompressible, so the solid and the solvent distances are fixed. These intermolecular forces are fixed. What do we say about the supercritical fluids? We can move them in and out and change the density. This is tunable. By changing those densities, those are adjustable, tunable. And then the intermolecular reactions moving in and out are also tunable. Important considerations. This goes back to, as Dr. Mukhtar pointed out as well, tunability, tunable. This gives us a great deal of understanding power. So, if we talk about manipulating the pressure, changing the density, this changes the solvating power. We can dissolve some compounds under this conditions, another compound under a different condition. We do this now with solvents. Acetone dissolves different things than hexane. Wouldn't it be nice if we could, and we do that by changing solvating power, by changing the solvent. It would be nice if we could go ahead and change the solvating power by changing the density like we just said. This gives us an ability to change the dissolving compounds, allowing us to fractionate, to separate. But all the time, how many solvents are we using? One, carbon dioxide. This is the power of supercritical carbon dioxide, because you can change the solvating power. So from one solvent, we have the solubility characteristics of many. This is a very powerful tool that you have in doing these kinds of separations. Let's use the practical example, as this is the system that is in the pap cup. Let's say we have compounds A, B, and C in pressure vessel. We start up the pump, we bring it to a high pressure. We see at this particular pressure, compound A still is not soluble. B and C are soluble. And then we come to a pressure regulator. We reduce the pressure at this point to something less. And at this particular condition, we've reduced the solvating power. By reducing the solvating power under this particular condition, B is no longer soluble. It comes out of solution. However, C is still in solution. We do it again, reduce the pressure, and this time, C is no longer soluble. We can do this, as Dr. Mukhtar pointed out, by having numerous separators for different conditions. Or, if we have one condition, one separator, we can change the conditions as the extraction partakes, goes forward. Lots of variability. And then ultimately, we reach the last point where we have a gas, and then everything will fall out, and then we go back and recycle the CO2, and the process starts over. Now, what I would like to point out, though, in a process system, we typically don't use one vessel. There's two vessels here to show you in a typical system. In this case, what we have is we will alternate preparing one vessel and unloading it, and while the other one is being extracted. And when that one is done being extracted, we will go ahead and load the other vessel and begin the extraction. Swap back and forth. So typically in a production scale, we usually see 2 and sometimes even 3 vessels, depending upon the rate of extraction. Now, there are some things that we have to try to pick those conditions to extract. And as Dr. Mukhtar pointed out in his paper, some of the things when you extract with solvents, you got everything. We saw the brown versus the yellow or the white, because everything was extracted. We pick the conditions where we find that we have the greatest amount of extraction of the compound of interest, but not the solvating power that brings along the other products. as we call them, co-extractable. The thermodynamics is also important. I'll give you an example a little bit later about lycopene. And then we need to discuss the kinetics of the material itself. Whether or not this is what we call solubility limited, or whether or not this is diffusion limited. If we have material that is deep inside of a material, inside of a seed, it takes a period of time for it to diffuse out, or for the CO2 to diffuse in. As opposed, if it was on the surface, it would then be pulled off very quickly. So some of the kinetics and the location is very important as well. As I pointed out, we've got, in our supercritical point, we couldn't reach methanol. So how are we going to extract polar compounds? Polar compounds, and as in the paper that Dr. Mukhtar gave, he talked about an extraction using a modifier. And that's exactly what we wind up doing. We typically use a polar compound to achieve an extraction of polar. We use a polar modifier to extract polar solvation. We add them to the CO2, and what we try to do here is form a single phase. Now this is important when you add solvents to the supercritical CO2. We saw before the supercritical point of carbon dioxide, for example here, based upon the pressure and on the temperature. This was the supercritical point. Now, as I said earlier, also, everything can be made supercritical. Let's say we have another solvent here. Its supercritical point is here. It is different. Now, so you can't use the condition of carbon dioxide, its supercriticality, right here, to understand that you will have supercriticality throughout. Obviously, as you move closer to 100% of this solvent here, let's say in this particular case it's toluene, you will have greater and greater supercritical conditions that mimic the toluene, this point. So as the concentration changes, the supercritical point of the mixture changes. It is this continuum here. So we look at this three-dimensional. If I would go ahead and point it out this way, and I put the toluene on this phase, and on this I have my carbon dioxide. Then if I look at it straight on here, this is the trace that I will be making from the combination, the mixture of the two. It will look something like this. This is an important consideration if you are close to the supercritical point. And many times when you're dealing with natural products, one of the things that you want to try to go ahead and do is try to keep the temperature down, because many of the compounds that you're dealing with in a natural product are thermally labile. That is, they will be destroyed if the temperature gets too hot. So most of the time, we either have to increase the temperature or increase the pressure in order to maintain that single phase. It's an important consideration. If you don't, you will have a two-phase system, as shown here. Now, all supercritical, I'm going to go through some of this more quickly. Generally, we can add any kind of organic solvent into the CO2 and it will be completely miscible. The temperature and pressure must be such that we have a single phase, like I just pointed out. What's really nice, especially when we're dealing with cleaning applications. Sometimes you have a circumstance where you're not going to be able to dissolve the polar compound other than using, say, a cleaning solvent like methanol. You can't get at it anyway. You can't dissolve anything. But let's say that you can use a small amount of methanol to do the cleaning. Instead of 100% methanol, you can use now a very, very small amount of methanol in order to do the cleaning. I give you the example, another very simple example that I give to people that are not chemists. I use the example of, let's say, how much water do I need to dissolve a gram of salt? If I have a gram of salt, it takes about 5 mLs of water to go ahead and dissolve this gram of salt. If I take this gram of salt now and bring in 2 kilos of very clean sand and disperse the salt throughout the sand, how much water do I need now? Considerably more. Considerably more, because now I have to pass through all of that sand. But really, all I need to do the dissolution is 5 mLs. But go ahead, put 5 mLs on the sand, and I won't do anything. Wouldn't it be nice if I had an inert agent that carried the water through? So now I can use substantially less solvent to do the same kind of cleaning. And this is another consideration in terms of how much solvent do you want to use to modify to extract the product out. You may not need it very much. But if you do, what's interesting is the solvating powers, even if you bring in very large amounts, 50 to 60%, it's been shown, that you still have the same solvating powers of the bulk solvent, the 100%. You can dissolve it in the same fashion. And the benefit is you get the diffusion characteristics of the supercritical CO2. Very important when you're dissolving, extracting out of natural products that have, for example, surface areas that are difficult to get at. And I'll show you some of that having to do with cellulose structures. We can determine what the amount of modifier should be by a number of different means. We can do this arithmetic calculation with the various moles. It's very difficult to do this. This is very good under theoretical conditions. But how many natural products do you know that have only 2 components? Not many. It just doesn't exist. So you can do this, but you can get an approximation. And if you're really smart, then you can go into equations of state. And I don't do calculus anymore. I forgot how to do that a long time ago. Now, some of you back in the audience may still like to do that kind of calculation. It's great for academic exercises, but really, this is merely a starting point for doing some of the calculations, doing some of the testing that you need to do if you're going to be using a polar modifier. Okay, should we take a break here? Okay. Or are there questions, on this section here?
Oh yeah. Which will be after the second one to maybe. Okay. إن شاء الله ربع ساعة بريك ونرجع ثاني نكمل محاضرة الدكتور. لأن حسيت إن بدأ تنام شوية. طبعا.
So we can start? Okay. told that I speed up all the time, so
أقل من سنتين.
دكتور هشام وتلفزيون عم يتداول.
أنا آسف. أنا آسف جدا.
I was told that I speed up all the time, so please keep me slower, okay? When, especially some of the things that coming now, I will pass over because we don't really have enough time to go through them all. But what I want to do is just give you an introduction to some of the points. So I will deliberately go very quickly over some of these and not talk about them, but you can see what is happening. Some of the diagrams I will spend more time on because these are some areas that I think you would understand and use immediately to be able to use in your work. Okay, what we said we would do in this list of things, let's talk about nanoparticles, production of nanoparticles. I got feedback here, okay. Making nanoparticles. Now the traditional way of making nanoparticles is we can do crystallization by adjusting the temperature and then adjusting supersaturation. We can use anti-solvents. These are ways of doing crystallizations and then reactions and precipitations. This is the ways of doing the traditional way of doing crystallization. And then spray drying. Particles are formed by spray drying as well, too, through a nozzle into the chamber. These all have some problems associated with them. There are some other ways of making particles as well, because we wind up sometimes with product contamination. They require higher amounts of energy. That means higher temperature sometimes, and if you have thermally labile compounds, this could be a problem. Usually, large amounts of solvents are needed also. Now, let's see what we have to see. There. Oops. I did it again. So all of these together will reduce the yield that you have many times. And then many times the particles are not uniform. They're either too large or too small. The distribution can be very varied. Another way of doing this, you can also micronize, that is to grind them, to crush them, to do milling, and these also have problems. There is thermal degradation in the grinding. And when you're dealing in the US, I know, when you're dealing with these kinds of degradation products, they have to be identified for the Federal Drug Administration in the US. All of these thermally degraded compounds need to be identified and then ruled that they are not problems in the overall drug. So with these problems, we have product contamination, high energy. I'm going to push that one all the time. Okay, I'm going to go through these quickly because I want to get into exactly how we do some of these, make some of these nano-sized particles. There are 4 different ways of doing this. Now, I did not come up with the names. These are names that are in the literature. But there's a process called RES, which means a rapid expansion of a supercritical solution. Gas is gas anti-solvent. PCA, precipitation by compressed fluid anti-solvent. I speak English, and I really don't know what that means either. I don't know who came up with these names, but we're stuck with them, so we have to keep using them. They use in the literature, somebody uses them over and over again, and now it's an English word. I don't know how it got to be a word. And then there's SEDS as well. That is solution, this is another mouthful, even for someone that speaks English. Solution enhanced dispersion of supercritical fluids. Wow. That being said, let's just go and I will explain what they are by the shortened version. For example, RES. Okay, Now, which technique do we use? There are 4 that are listed, and there are more as well, but these are variations of the same sort of thing. But these are the basic ways of making particles using supercritical fluids. The big question is it soluble in CO2? If it's soluble in CO2, then we will typically use RES. If it's not soluble, then we've got to use one of the other techniques, gas, PCA, or SEDS. Now, in RES, what we do is we load the compound, and you can read this along with me. We load the compound, we pump in the CO2 to dissolve it, and then what we do is we depressurize through a nozzle. And then this supersaturation occurs, and the solute then becomes particle. Let's look at it this way, through the diagram here. Here's what happens. We load up our compound. We want to keep it homogenized, so we put a stirrer in this as well. We can put a stirrer in a pressure vessel. There's no problems in doing that. It's an engineering, but you have to go ahead and do it. Even though you have pressure vessels that go to 1,000 bar, we can also put stirrers on these so that you can ensure that you've got a homogenized sample, a homogenized mix. So we bring in the CO2 at this point, and then the CO2 goes ahead and dissolves the compound, and then all we're doing is spraying it into an ambient state. Spray it in, and then we meter out, and the CO2 either gets recycled or it gets vented. Now, very straightforward. Now, we can put this in air, here, and in air, but one of the things that's important to do, and I will talk about it a little bit on a laboratory scale, is real easy just to coat the sides of this. And this is one of the things when you read literature about doing RES, it's almost like spray drying, but it's difficult because the particles are so small, difficult to remove from the side and to capture easily. So we have come up with some techniques for doing that. Some of that has got to do with putting it into a bag that you can go ahead and now easily collect the particles this way as well. You can also go ahead, instead of doing it at ambient air conditions, you can go ahead and spray this into a liquid as well. An aqueous solution is often what is used. Some of the problems that you have, that if you put it in this system here, these particles often agglomerate. So you may think that you have a material that is, you think you're going to be making the material at, let's say, 100 nanometers, and actually it agglomerates together, and you have something that is 20 microns, as opposed to 200 nanometers. They agglomerate very easily. There are ways, this is one of the reasons why you disperse them in a liquid, because they will not agglomerate as quickly. And nowhere, I can vouch for the fact of the hundreds of papers that I've read, nowhere does anyone really talk about that on an academic level. But on a production level, it's very important if you're going to go ahead and have these smaller particles. And here are some examples of some of the particles that have been made in sizes of these. And the distribution of these is quite narrow. It's a pretty good distribution. The mean is very narrowly defined. I'm not going to go through this. One of the things that that's important to do in the system, and we do this, and I use the laboratory system, but it's the same whether or not you're doing laboratory scale or whether or not you're doing larger scale production. The same kind of holds true. What's important to go ahead and do is to put the sample in, but to develop a steady state circumstance with the CO2. That is, you bypass the CO2. You bypass the particle vessel that you're going to do, the dissolving vessel. This vessel here, you want to bypass that initially, pass it through the nozzle. Now that you've established that as a steady state, now switch the valve on. And now you will get particles, and you will not get clogging if you go ahead and this is very easy to go ahead and clog. So run the system beyond the vessel to begin with. Okay. I'm going to not go through this. These are just the parts. Let's talk about gas now. Gas anti-solvent. This is now one of those circumstances where the compound is not soluble in CO2. So we have to use a different technique. We have to use one of the techniques that is gas, PCA, or SEDS. SEDS is a little bit more of a complicated, we'll just touch upon that one. But let's talk about gas. This is gas anti-solvent. And anti-solvent techniques are used a lot even without supercritical fluids. But I'm going to use it here to describe how the particles are made. What we do is we go ahead and dissolve the compound. It's in the organic solvent, okay? Now, we pump this, we fill the vessel with a small amount of CO2. Then we go ahead and introduce the supersaturated solute. And then let me show you this way, instead of carrying it through. Here's what we do first. We go ahead and, here's our solvent and solute. Remember, our solute is not soluble in CO2 this time. So we have it in solution here. How are we going to make particles? Now, what we wind up doing, we pump it in, small amount. Then we bring in the CO2. And what happens is the solvent will dissolve into the CO2. Now, with it dissolving into the CO2, there's not enough solvating power to keep the solute, that is the particle, in the solution. So it will begin to fall out of solution. Now, I want you to keep in mind, one of the very important things that we talked about early on, and Dr. Mukbar told you about this as well, and I've emphasized it over and over, tunability. Now, we can change the solvating power of the CO2 based upon the pressure that we put in there. So, this is a very powerful tool that you can dissolve the solvent in the amount that you want, and the rate that you do that will determine the size of the particle. So, faster, just like any kind of precipitation, if the precipitation occurs quickly, then the particles will be smaller. And it's the same situation that you have here. But now you have a means of controlling this by controlling the pressure, the solvating power. You will determine the rate of dissolution of the solvent into the CO2, and then having the solute fall out of solution. Now, I said a lot there. Do you understand that? So once you're done, then you just drain this off, and you have your particles. Now, as you continue the CO2 flow through there, then obviously you're drying it as well. Then we just discard the solvent. Now, here are some examples of some of the things that have been made in this fashion as well, pharmaceutical compounds. And these are all in the literature. It is learning the technique itself, having the patience to go ahead and follow through what you're doing, but then having the piece of equipment that you have that allows you to go ahead and control these parameters. Gas SAS. Again, like I said, I don't know where they come up with these names. But here's what we're going to do. We have our compound that is dissolved in the organic solvent. This time what we wind up doing is we fill it with CO2. We're going to do it a little bit backwards. The first time we filled in the solvent and the solute and then brought in the CO2. This time we're going to go ahead and put it in CO2. And we're going to keep the CO2 flowing. So here's what we're going to do this time. CO2 is going to flow. We do this on a dynamic basis. Now you can see what's going to happen here. Now if you've got a lot of solvent, this is the way to carry it away. And the rate of flow here is very important in terms of the amount of solvent that is immediately going to be pulled out of solution and causing precipitation by the solid. So if we continue this, now we introduce our solvent and solute. And we spray this through a nozzle. And again, the CO2 is passing through. The solvent will dissolve into the CO2. It is carried away. There is not enough solvating power in the original solvent anymore, so you get a case where now you don't have enough solvating power and the precipitation will occur. Again, the amount of solvating power of the CO2 you can control by the density, that is, by the pressure. The tunability factor comes in again. So I'm going to throw a lot of things at you, but think about the fact that all of these kinds of ways that you can now control solubility. And this is the important part of this. This is a very powerful tool to be able to use this. Wide variety. And initially, when this technology first started being used, when I told you about the decaffeination of coffee, it was really, let's use it as opposed to a solvent. But now what's happened is researchers have used the technique and the technology more and more, and quite frankly, the instrumentation has improved, and the technology of the engineering has improved over the years to allow these kinds of things to be done more and more precisely. And believe me, we're not alone. There are many other companies that go ahead and work in this area as well. I'm slowing down again. There are many other, and there are many researchers that have built systems on their own to try to do some of this. But so the technology has moved forward, but these are some of the techniques that are now possible. So now then ultimately you drain all the solvent out and continue the flow and then discard the solvent. A couple of examples here. These are some of the things that have been used to go ahead and do. This is a compilation from the literature of a variety of different kinds of drugs that the particles have been made of these kinds of drugs. One of the big areas is inhalation, particles for inhalation. When you have the inhalers, like for asthma, for example, albuterol. This is one of the ways of doing this. Also, what's become very and there's a great deal of secrecy about, because the drug companies keep much of this information for themselves. But many of the cancer drugs are not actual solutions. They are really suspensions, and then they are injected in. So some of these suspensions, these are actually particles that can go ahead and control very precisely. You want to control these so that they can be carried through in the body, into the veins easily. So particle size is an important consideration along those lines as well. So now, let's see. I just did that one, didn't I? No, okay. I want to do PCA. Okay, what we're going to do in this one is we've got CO2 flowing again. This time what we're going to do is through a coaxial nozzle. Now, I'm showing that right here. So we do the same thing, bring our solvent and our solute through, but this time, instead of just putting it in, what we're going to do is spray it through this nozzle, and this gets yet some more mixing. So what I did previously is I had the CO2 flowing. Now I've got these flowing at the same time. The CO2 and the solvent solute flowing at the same time through the coaxial nozzle. Here's what if I carry this through here, look at the nozzle. The solvent and the solute are in the center, and the CO2 is in the outside of the nozzle. We spray it that way. Now, here now the important part is the mixing and the interface that you get with the nozzle. Just another technique. We're still using the anti-solvent technique here. But what we're doing is causing different mixing. What this does is not only change the size of the particles, but it will also change the morphology of the particles. Depending upon the nozzle you use and the size of this, the configuration of this will change the morphology of the particles as well. Without going into a whole host of different nozzles on this outside of the scope of this talk, you can go into the literature and see some of these that have gone ahead forward. I'm going to move past SEDS because that's really what we're doing now is another coax nozzle, and now we're using water to dissolve into a solvent, into the CO2. It's just on and on, more of the same thing. Okay, any questions? First of all, I should have started the talk with any questions from the first hour. Sir.
So I have one question. Is it possible to use the supercritical fluid in the extraction of liquid culture, for example?
I'm sorry. Can we... Oh, wait.
So usually we are using solid materials for the extraction using the solid phase supercritical carbon dioxide. Is it possible to use liquid for extraction?
Use liquid carbon dioxide?
Yeah. No, for extraction, for example, for working with bacteria, we have culture or media, and we have a natural product or secondary metabolite in the media. Is it possible to extract these compounds using this technique?
To extract liquids. I will talk about it at the end of the talk. And then I think I will answer your question that way. Very shortly, yes. But then I will show you a couple of techniques to extract liquids. Absolutely. Question from the first hour? I should have started with that, I'm sorry. I totally forgot. You should have reminded me, Ahmed. It's all your fault. Yes?
Are there any disadvantages of using supercritical carbon dioxide?
No, it's wonderful for everything.
Using it for nothing 100%.
Nothing is better than using supercritical carbon for everything. For driving your car, you don't have to use gasoline anymore. It uses supercritical carbon dioxide. You know, you can eat it. You won't gain any weight. Obviously, there are problems with supercritical carbon dioxide as well. I mean, nothing comes without some disadvantages. Of course, there are some disadvantages. The major disadvantage is the fact that you have a pressure vessel. You have to deal with higher pressure. You can't do this work under ambient state. That is the major drawback. And when you're dealing with a pressure vessel, this initial technique usually tends to be more expensive. So that you're not dealing in an open air ambient state, where you have a thin wall. You know, you're just dealing with, you could deal with potentially doing some reactions, and a polypropylene or polyethylene, vat, just an open container to do some of this. You can't do that. When you're dealing with pressures of 700 bar or 1,000 bar, I mean, we're dealing with wall thicknesses that are this thick in order to hold the pressure. This is necessarily more expensive. So you've got to deal with that. Then you have to also deal with the length of time that you cause to depressurize. You just can't open the vessel. If you just open the vessel like this, that is like having a sonic boom, boom. It will really, so there is some depressurization. And then there are some engineering things with the depressurization that you have to take consideration, is the fact that this will cool and it will ice up. So you've got some considerations having to deal with the cooling, what's called the Joule-Thomson effect, that you've got to have engineering to ensure that when this cools, you have enough heat so that you don't get freezing of this. So all of these have got to do with the dealings of pressure and the initial capital cost. But we've calculated, depending upon the value of the natural product or the products you're making, you can get a payback of very large systems. We did the most recent calculations of dyeing textiles. Of the dyeing of textiles, we can get very quick paybacks. We can get paybacks of 3 years for very large production. Now, dealing with textiles, that's not a very expensive commodity. If you're dealing with a high-value drug, then you can imagine your payback is going to be much sooner. Did I answer your question?
Thank you.
Sure. Yes. Yes.
Thank you very much for the impressive lecture that fits into many disciplines in science. From my knowledge and from the material science point of view, the nano scale is less than 100 nanometers. Okay. You represented the products in the micro scale, not in the nano scale. So my question is this technology suitable to produce products in real nanoscale to use as products for delivery, drug delivery, and these products?
I'll be very frank with you. There has not been good results when we're dealing with organic molecules for pharmaceuticals. The results have not been that good. And the problems that you have most of the time have got to do with agglomeration. That is, the very small particles will now stick together. Now, people are trying all sorts of techniques subsequent to making the particles. For example, putting ultrasound into the collection area. So there is work that is being done in this area to prevent this kind of agglomeration. You can get some of this not happening if you go ahead and do it in a liquid. The example that I gave with RES, okay? It's very difficult to do with gas PCA except where you can dry those completely. You still are often stuck with agglomeration. And that is the major issue. Now, there are some inorganic, you have a much better chance of doing some inorganic metals, but now we're into a much different kind of technology. We're no longer using carbon dioxide to do this, but now we're into doing this with water, supercritical water. And that becomes even more complicated to go ahead and do. But they have developed nanoscale metal particles outside of doing it by other than by furnacing. And again, if you do it by furnacing, you get usually a wide range of particles. You can keep the mean very narrow by doing it this technique. But there's an awful lot of work. It's still really experimental. I'm not familiar with any kind of production scale that is putting it on the scale of nano. Now, the big problem that we have here, and I will be the first to admit, when we work with a pharmaceutical company and they begin to, and they buy a piece of equipment from us and we work with them for a period of time, they then say, okay, that's enough, and then they keep all the information for themselves. They may have developed some techniques to do that, but they're not publishing that. So we kind of, and quite frankly, I suspect that it's being done, but I can't tell you other than some of the techniques that I've heard that are being done. We have not done it in our laboratories, but for example, the example of the ultrasound, for example. There are some ways of doing that, okay? I'm sorry I couldn't answer any
No
better.
problem, it's okay, very nice answer. And I believe to avoid all this agglomeration, you can use the technique for blending these products with other to increase the surface area of absorption and so on, from my point of view.
And these post-treatment examples are perfectly valid. I absolutely agree with you. You know, these are ways to do it. The generation of the particles, you can go ahead on the scale that we're talking about, but they still, if we use some of the techniques that you pointed to, are excellent ways of ensuring that you don't get the agglomeration.
Thank you very much.
Sure. Okay, so we move on? Okay, general processing, natural product. I'm going to skip through a lot of this because I want to get to, well, here are a couple of, these are systems, these are larger scale systems. This is the 250 liter system, and then we have 500, that is two 250 liter vessels, a 500 liter system, and then you can have 500 liter vessels. And again, most of the time, as I mentioned earlier, we're talking about having two vessels here. A couple of the areas we talked about, food improvement. And as Dr. Mukhtar pointed out, the same brown, we have the same sort of thing here. When you do an extraction with a solvent, remember, that solvent can only dissolve everything. It is going to dissolve many more things. You cannot be as selective. One of the things that you can do with supercritical CO2 is you can pick the solvating power to optimize the compound that you're looking for and leave behind the what we call co-extractables. So selecting that is exactly what happens. And as a consequence, you wind up with a better product. Exactly as Dr. Mukhtar had pointed out as well. A couple of other areas, this is one I wanted to talk to you about from the first hour. Fat reduction, but I wanted to talk to you solvent-free products, but there it is, okay. This is macadamia nuts, and this is really quite interesting to be able to go ahead and do this. Is macadamia nuts, you may be familiar, but any tree nuts work the same way. You can do this sort of thing, some to a greater or lesser degree. But what's happening here is macadamia nuts, the company does a partial extraction of the oil in the nut. Now this is very clever. You take only some of the oil out. Now, it's been determined that apparently about 2 or 5% of the population can't tell the difference between the nut with all the oil and the nut with some of the oil removed. Can't tell the difference. So now what the company has been able to do is remove some of the oil and sell it, and then also sell the nut. So now instead of selling all the oil or selling the nut, they're able to sell both and make more money that way. So this is partially defatting. It's a very clever way of doing it. And remember, if you were to do this with another solvent, the residue would be there. But since you're using carbon dioxide, and when you come back to an ambient state, back to 1 bar, there is no residue. The CO2 is a gas. So no residue, you've got a product that tastes like the whole nut, and however you've been able to go ahead and pull some of the fat off that you can sell in a secondary market. So this is something else to consider along those lines when dealing with some food products. Nutraceuticals, we've talked about a little bit. These are into flavors, fragrances, spices, herbs, nutraceuticals, colors, lipids. I'm going to go through this because we've already talked much of this. I want to get into and just keep repeating this. I don't want to do this screening. I want to get into talking about essential oils.
This is very important for us.
Essential oils, yes. Let me just briefly touch upon this. Dr. Mukhtar mentioned a static and dynamic. Let me explain briefly what that means. Static is what and those of you that have worked with supercritical fluid know this immediately, but those that you haven't, all it really means is a static extraction is where we go ahead and introduce the vessel into the system, and then we bring in the CO2 to the valve, fill up the vessel, bring the CO2 in, and leave it there. It's analogous to having your tea and putting the tea bag in and leaving it there. Dynamic is what we wind up doing is we flow the CO2 through all the time. And there's reasons for doing this. It's got to do with whether or not we're talking about solubility limited or diffusion limited, and I'll talk about that in a few minutes. But very simply then, the static, we eventually then come to the point where we let it sit for a period of time. As some of the examples that Dr. Mukhtar had, we would let it sit there for 30 minutes, let it, just like the tea bag stays there for 30 minutes, and then you take it out. It's the same idea here. You let it sit for a period of time, and then you go ahead and flow it out. Dynamic extraction, like I said, is done on a continuing basis. That's the difference. Okay? And now, I'm not going to go through this part of it. It's somewhat obvious. Maybe I will. A couple of years ago, we had I talked mostly, it seems obvious, but some people don't realize to do this. It's when we talked about changing the solvating power, my example of ABC, I started with high solvating power and then reduced it, and then I got precipitation with B, went reducing the solvating power again, and then I had C precipitate out. You can go in the other direction too. You can start with a lower pressure and then go to a higher pressure, you just have to remove it. And that's really what we're doing here. So we start with a static extraction, and on a laboratory basis, we had a couple of years ago, we had from a requirement from the National Cancer Institute in the US. There was a requirement, we had a contract to do, and I can't remember the exact number, we probably had something like 5,000 or 10,000 different samples. And these were samples that was a lichen that may have been from Greenland. It was a root from a tree in the Amazon. It could have been a bark from a tree that was in South America, or a leaf that came from Southeast Asia. We had no idea where these were from. And what they were looking for is do an extraction of the various compounds here, and then they had a protocol where they would investigate if there was any anti-cancer activity. So what they were looking for were all these individual fractions of these natural products, with the idea that there may be something in there that they were interested in for anti-cancer activities. So the way we set this up was we set up the laboratory instrument, but instead of cascading it down like you do in a production scale, we went the other way. So essentially what you wind up doing is you put your sample in, our samples of A, B, C, and D, for example, and then we do our extraction at 2,000 psi, you see here. We're at low pressure, so we're not starting with high pressure going down, we're starting with low pressure going up. It's obvious, and I won't go through this over and over, but essentially what we're going to wind up doing is we do the extraction, perhaps, at one time a little bit of static, and then we go ahead and do some dynamic on this, and we can see that at 2,000 psi, only one compound is going to come off. We see C comes off. And then we remove that. We don't mix it. We remove it from consideration, from collection, and then we just increase the pressure. Now you can see we moved it up, and now we just do the same thing. We do it at 5,000 psi, we do it at 10,000 psi. And then each time separate off the individual components. So this way you can collect each of the individual, and then for the polar extraction, we introduced a modifier. And then collected it in that fashion. So this is what we wound up doing. We sent these individual fractions, all the different compounds, based upon the solvating power of the CO2 by manipulating the temperature and pressure. We had a protocol set up where now we can extract all these different compounds, not knowing what they were. And then the NCI did their own work to see whether or not any of these compounds had any anti-cancer activity. And if they did, what then happens is this is a screening method, and then they sent back to us and they said, okay, here's some more of this sample, or they collected it or did something else, and then we did that on a larger scale. But this is a very quick, down and dirty way of screening compounds. All right, I'm not going to base more on this one. Okay. We've already talked about much of this. I want to talk about, we talked a little bit about particle size. I think what I want to do is I want to talk about particle size. This is a little bit important as well. You want to, and Dr. Mukhtar put this also in his talk, talked about the particle size being of a particular size. And this is important because you want the mass transfer to happen as quickly as possible so that there is a low diffusion, that the particle size is such that anything that is in the mean distance to the CO2 is decreased by small particles, smaller particles. However, there is a challenge to this as well. If you go ahead and make the particles too small, then you run into problems such as channeling. What will happen is the CO2 will not move directly through the entire bed, but will move to the path of least opposition. There is no opposition, so it will channel, and now you will get an incomplete extraction. This is very important because many times you'll say that the extraction didn't work at that. This is one of the major things that you see when people say it didn't extract very well, and you know that it should have. Then you suspect quite a way, very quickly, that there's been channeling. Now there are some engineering ways to overcome this sort of thing. The use of baskets and the forcing of the packing, consistently packing the material down into the vessel, all of that helps in terms of stopping the channeling. Typically we're looking at mean diameters of this size. Optimum dimension, certainly you want to get rid of water. Water does not aid at all. The drier, the better. Okay. All right, I'm going to talk about essential oils here. A couple of examples of essential oils are, limonene, chamalizine, and citron. These are just, there are hundreds of essential oils, as you all know. And they, normally, you can go ahead and squeeze them out by expression. This is what you normally see lots of, or by steam distillation or a solvent distillation. Most often, steam distillation is used to extract essential oils. The steam distillation here, this is probably the most common way of doing it. But the problem that you have with steam distillation and solvent extraction, these are the raw materials, potentially could be all of these. Let me come back to steam distillation. The problem that you have with steam distillation is that you now are dealing with a very high temperature. You're dealing with 100 degrees C and more. And the problem that you have at this point is that many of, as the perfume industry calls the top notes, these are destroyed or they're carried away in the steam, and they're not easily recoverable. So you don't get anywhere near as good a product as you might. These are lost, you know, again, because they're thermally labile, we're dealing with a high temperature, or they're carried away in the stream. Now, from remembering what the supercritical point was for carbon dioxide, who remembers what it was? The temperature.
31. 31.
Who said that? Yes. Who said that? I wish I had a gold star for you. Very good, perfect. 31. I mean, that's less than body temperature. So we're not dealing now with high temperatures. We're able to go ahead and capture these at a very, very low temperature relative to the 100 degrees that we're dealing with essential oils, dealing with steam distillation. We can make, the industry can make a concrete, and this is the combination of the wax and the volatile oils, and this is the concrete. This is often, the concrete is done by an ethanol extraction, often done this way. And the industry still does this because it's very cheap and easy to go ahead and do. Supercritical can do the extraction, or we can start from the concrete. Or as the French say, the other English is the concrete. So we Americans bastardize the name, so we just say concrete because that's the English that we have. So, so we could say concrete or concrete. This is a paste. Now we can do the separation of the essential oils this way. Am I getting too close? We can do the separation of the essential oils this way, or we can take it immediately from the raw material. Either way, this is what we have to go ahead and do. I told you, this is thermal degradation, low contaminant. We put the oleoresin into the extraction vessel. Now this is a thick paste, so we have to disperse that a little bit. Typically what we wind up doing is we may use something like inert glass beads, is just kind of disperse the oil on a mass of glass beads. All that's going to be washed clean by the CO2, but this is a way of dispersing it out so that you can get a better extraction of this. Now, for the most part, what I've talked about when I gave the examples of the A, B, and C, I talked about separators where we're talking still supercritical carbon dioxide. So I was raising the temperature, raising the pressure. Now, I don't have to do that. We're going to separate the waxes from the essential oils. You've got this piece of equipment that is capable of running a wide range of different kinds of temperatures and pressures. Take a look. Here's the extraction pressure, 80 bar, 40 degrees C, supercritical. Flow rate, look at this separator number 1, 80 bar, look at the temperature. 0 degrees C. That's not supercritical. We've now chilled that first separator and made that liquid CO2. And then we go ahead and vent that. So if I put this in motion and I go this way, I introduce the concrete or the raw material, either one. Doesn't really matter because I'm going to pick it all up in the supercritical. It's going to dissolve both the essential oils and the waxes. So they are dissolved into the system, running the CO2 through this, and then bringing it up to temperature and pressure. I go ahead and flow the CO2, pass it into that first separator, and now I have a chiller over here. I put refrigerant through this, and I wrap it around here, and I'm chilling this vessel to bring it down to 0 degrees C. And at this point, the supercritical CO2 becomes liquid CO2. The waxes are not soluble in liquid CO2. Many of the essential oils are. So in this particular case, I've now separated the waxes. They will fall out of solution, and then I go ahead and depressurize to a gas, and all the essential oils will come out. So my point in mentioning that you can easily separate these two, we're talking solubility all the time. We've talked most of the time with supercritical by changing the solvating power. But there's nothing that says that you can't bring it all the way back to a liquid. And then there are some things that are not soluble in some liquids. In the case of waxes, they are not soluble in liquid CO2. So they typically then will fall out of solution, and you've done the separation this way. You've fractionated them. We take a look at the analysis of this. Let's take a look. Here we have jasmine extract. Here it is before, and here it is without the waxes, the GC trace. And if we do tuberose, we can do the same thing. You see here it is before and after. We've gone ahead and separated the essential oils from the waxes as well. And we've done it, again, on the basis of solubility. So, summary, we can go ahead without any kind of thermal degradation, extract the essential oils and the waxes, and the two are completely separated. But instead of now of keeping it lower pressure in the supercritical state, we're taking it all the way to liquid, chilling it that much and letting the CO2 go into a liquid state, and the waxes fall out. And again, we're free of any organic contamination here as well. Now, what happens is, by doing it this way and not using solvents to do this, the smells do not have any overtone or residual smell of the solvent. Okay. The extractor vessel, again, remember, this is what we did, the first extractor vessel and then a collector on this. This is the normal system to go ahead and do this. This is the system that we normally have for supercritical fluid. So the traditional sense of doing this, I don't want to do, the traditional sense, go backwards here. The traditional product separation would be reducing the pressure and heating that second separator, that first separator. And then going to a gaseous state and heating again. When we do essential oils, the big change is, instead of heating this separator, we're chilling it. Now we get liquid CO2 and then gaseous CO2 for the essential oils to fall out. This is a typical smaller system to do concretes. You can see here's the dissolution vessel, Here is the wax separation. You can see this is now chilled. And then here is where we go ahead and gasify. Any questions on that? Yeah. Instead of waiting to the end? Does anyone have any questions on the essential oils? And the fact that you don't have to go stay with supercritical, you can go all the way to liquid as well. There's no reason to go ahead and limit yourself. I'm just trying to give you opportunities that you can go to many, many different ways that you can use solubility in the supercritical state, but then also in the liquid state. Seed oils. These are the ones that are most often used with hexane extractions. Seed oils are often, for example, the major ones, for example, in the U.S., corn oil is done with hexane extractions. And the problem is that we always have here is the residue. And typically, although we've gotten better and better at this, even with vacuum distillation and vacuum pulling on this, we're still often left with 500 to 1,000 parts per million residual solvent. The industry is getting better and better at this, but there's still that residue. The big thing to keep in mind when you're dealing with seed oils is the higher the pressure, the better. So we're dealing with regular oils, cottonseed, whether we're dealing with corn oil, all of these seeds tend to be extracted using a higher pressure. And this is work that was done by a friend of mine at the USDA, who also I've done some work together with, is Jerry King. He's published a great deal. He's most recently been at the University of Arkansas. But he did this work back, even at year 2000. He had done this work. If you see, here's the triglycerides. If you look at this kind of pressure, typical what you see in a lot of systems, you see the independent of the temperature. You get a very low yield. Now, you can get it all out, except that now you're going to take a longer time to do it. It is going to extend your time of doing the extraction. Whereas if you take a look at 700 bar, you can see the solubility is much, much higher. And the rate of extraction is much faster. So dealing with seed oils, the big thing to keep in mind, higher the pressure, the better. Other examples of this, here's some sandalwood also. The best pressure, percent recovered, here we are, 800 bar. I want to talk about a little bit now, pressure, not all the time. It's also interesting that you can use temperature, the kinetics, and lycopene is another example of this. Now, lycopene is in tomatoes. We can increase the rate of extraction of lycopenes using a co-solvent, but what happens is this gives you a poor extraction, brings on lots of other products as well, is not as clean as doing it with supercritical CO2. You can have a lower pressure, but at 40 degrees the extraction is pretty poor. Now, you get some improvement with increasing the pressure, but temperature has a greater effect. And if I show you here, at 100 degrees C, now remember, if you have compounds that are thermally labeled, you won't be able to use this technique, but lycopenes are not. So now use temperature to your advantage. You can see at 110 degrees, look at the extraction time. In 40 minutes, you've got 100% out. Temperature can be used to your advantage as well. Another little technique I want to show you is dealing with cashew nut oil. This is the cashew nut, the oil that is not in the meat of the nut, but in the shell. This is, and I'll show you here, these are anacardic acids. And these are used in a wide range of antibacterial configurations, antifungal, and actually in some of the resins and coatings on natural products. A couple of examples, but here is the cashew, and this is the area that we're talking about. The area between this epicarp and the endocarp. This whole area here, this in purple. This is the cashew nut shell, and this is a very valuable product. Getting this out and not taking it out of the nut is an interesting, difficult problem. An easy way of doing this is we have an extraction mechanism where we keep it at a lower pressure. The CO2 penetrates into this shell, inside of this vesicle, and it penetrates this. And then what we dissolves the oil, and what we wind up doing in this particular case is we depressurize, causes it to swell. We depressurize rapidly, and it ruptures the vesicles. So now here, what we're doing is you don't have this kind of advantage when you're dealing with liquids. We're going to take the physical properties of the CO2, that is the gaseous expansion and then the depressurization. We're going to cause the bends in this material. It will rupture, and now it's ready for solubility and flow. Questions on that? A couple of examples as to all the different things that you can do dealing not only with solubility, but also dealing with the physical characteristics as well. You heard this term before, anti-solvent. Now this time what we're going to do is we're going to dissolve the natural product in a solvent because it's not soluble in the CO2. And we're going to do exactly the same thing. We're going to go ahead and extract lecithin from the triglyceride oil. The triglyceride oils we saw are very soluble in CO2. So what we're going to wind up doing is, normally this is extracted with acetone. Not a very good candidate, not from an environmental point of view. Lecithin is insoluble in the acetone and it's time consuming. And then we have these characteristics, the 40 bar and 40 degrees. I want to show you here. So we have our lecithin and triglyceride. We pump that into our vessel. And remember, the lecithin is not soluble. So we're going to do an anti-solvent. The triglyceride will go ahead and dissolve into the CO2. The lecithin will not. It will fall out of solution. The same way that we did particles, but now you can go ahead and do this with any kind of natural product as well. It's another technique for doing this sort of thing. It's extracting a liquid. Okay? And then you go ahead and recover the triglycerides. I want to talk about this last one, countercurrent. Just demonstrating again the wide variety of things that you can do with this technology. Countercurrent is dealing with a liquid. We're going to go ahead and have something that is dissolved in a liquid, and then we're going to extract it on a continuous basis. We have a long pipe. Looks like a long pipe. This typically, depending upon the extraction mechanism itself, is going to be anywhere from 3 meters to 5 meters. I think the biggest one that we've built has probably been a 6-meter column. 6 meter. Now, I don't want to imply when I say column here, do not think chromatography column. It is not packed with any kind of chromatographic material. It is packed with something that you would causing the flow to be moved around. Very similar to inert packings that you have in a distillation column. You're looking to make a tortuous path of both liquids. So what we have in this particular case is we bring in a liquid with an extract in it. Something that we want to go ahead and remove. Comes in the top. In the bottom, we pump in supercritical CO2. It mixes along the way. Very similar to, remember in your laboratory when you have a separatory funnel. So you're shaking the tube. Now you get mixing, and we're doing the same thing. We're doing exactly the same thing. The liquid, however, is moving down this way. Now, if there's a greater propensity or a greater opportunity for the solute to be dissolved in CO2 than in the solvent, then it's going to move into the CO2, just like in a separatory funnel. We're doing the exact same thing. Now, what we do in the middle here is we have material in there, inert material, so that we make the path move like this. Now, ultimately then, the CO2 comes out, and then we can go ahead and have the extract in it. And then at the bottom, we have the liquid that is free of the extract. Now, remember, we can do this over and over, so we can reflux. So if we didn't get it all out here, we can introduce it back in. Or we can just continually do this. So this is a continuous way of doing extractions. Now, keep in mind again, one of the very important parts, and I'll drive this home over and over again, is the fact that by changing the density of the CO2, we change its solvating power. Now, I'm going to show you a lot of calculations. I'm going to pass through all of that because it really comes down to making it, all of these calculations, and I would go through that, but it's getting late, and I want to move on and just show you conceptually what we're doing here. Now, first comes to mind as to, wait a minute, this doesn't make any real sense to me. How can this flow this way and this flow this way? You know, from just thinking about it, that doesn't seem to work right. There's, you know, even though you're pumping one this way and you're pumping one this way, why don't they all go up or why don't they all go down? You can make these calculations, but essentially what we're doing here, conceptually think of it in this qualitative way. What we have is a denser liquid falling through a less dense medium. That's all we're doing. We're controlling the density. The liquid, we're not controlling that density. That could be anywhere from one, wherever it is, wherever that density is. But by controlling the density of the CO2, and that density of CO2, remember, we can have that to be 0.1. Very, very low density. So what's going to happen is this will fall through. And as it falls through and moves through, then the extract will be pulled into it. By changing that density, based upon what the liquid density is, we will go ahead and get an efficient extraction. Now, like I said, there's all different ways of measuring this and doing these determinations with a variety of different kinds of equations to work out the densities, the separation factors. All of that can be all nicely worked out. I'm not going to go over that right now, but this really comes down to conceptually what I just described. We're taking a liquid that is more dense and passing it through the supercritical medium, which is less dense, and then having that solute that is in the liquid pass into the supercritical fluid. Okay? So, yeah. There's an example of some of the inert materials. Sometimes they're just various glass beads or they're steel balls. They can be any number of things Just you're looking to go ahead and disrupt the flow to get the maximum amount of interaction between the liquids. That's the same sort of thing when you're doing this with a separatory funnel. How long are you going to shake it to get the maximum amount of transfer of the solute into the other solution? You're doing the same thing here. And a couple of other factors in the equations that I passed over. The length of the column will also be important for that as well, to get the maximum amount of interaction between the solute and the supercritical CO2. Okay. Now, I've got to give a paper here in June at the ACS Green Chemistry. And one of the paper that I'm giving here is work that we wound up doing with steam distillation, the distillates. Coming off of this is an environmental problem. These have to go to the waste treatment facility, these floral waters. You've got essential oils, all that sort of thing is now has to be dealt with from a disposal point of view. We did some work here where we're taking this waste stream, which has got liquid and essential oils in it, running it through the column here. And where we're recovering all of that extract. Remember, we're getting out of this the essential oils and the waxes, because they're both soluble in the CO2 supercritically, and then we go through the separations that I showed earlier about essential oils. So here's an example where you could go ahead and get more product and not have to spend any money for the sewage treatment, the wastewater treatment facility. One last example, a couple of examples. This is palm oil. I was talking to a group, this is a system that we put as the 3-meter column that we put in for, I think it was 3 meter or 5 meter, column that we had for the Malaysian palm oil board, where the extraction of vitamin E out of palm oil. And it was done in exactly the fashion that I mentioned here. Then I want to show you one last thing. And these are all extraction of fish oils. How complicated, but then how elegantly simple some of this as well, is that what we're going to do here is we have 2 countercurrent columns. And this is a continuous extraction all the way along. Extraction of fish oils, this was done up in Canada. We did this, where we're extracting omega-3 fatty acids out of waste fish oils. Now the fish oils, as you know, prevention of heart disease, these triglyceride oils have to be treated. We have to cleave off and then make the fatty acid ester in order to go through this separation. And I won't go through all of that, but ultimately what we're going to find is two-column countercurrent system. And what we wind up doing, here's our 2 countercurrent columns. Here, separators, collectors. Now, we feed in the esters at the midpoint, and we introduce the CO2 here. We begin the extraction, the countercurrent extraction. Remember, this material is going to fall down this way, and we're going to go ahead and extract it off here. Goes through the separator. This gives us an opportunity to reflux. If we didn't remove it all, we start refluxing. All right? Now, we took off, let me back up because I missed that. We're refluxing. We did remove the C16, C18 fraction, this extract. That's not the important one. the ecodenoic and icodenoic acids are in this fraction here. Now, this fraction, these C22, 21, or 22 and 20 intermediates, come in, they get introduced to this one, in the middle of this column. Introduce the CO2 in the same fashion. And now we do the same thing. Refluxed again, and this time we separate out the two fractions. This one gets separated out from this separator, and then the balance, the C22, gets extracted here. So here we've separated these two fatty acids, the omega-3 fatty acids. And all of it is done on a continuing basis. Feed it in, continues to roll on and on and on, and then we have those separations. Okay, first of all then, we all know now what to use a supercritical fluid for, right? Let's hope so. I want to say, Shokran, thank you very, very much. Questions? Questions? Okay.
فيش أي أسئلة؟
Thank you again really for fantastic lecture. And as Egyptian, I feel very, very proud that I could see applied work here and the connection between the university and the company to see such a great work. This is really unbelievable. This is the first comment.
It is my pleasure.
Second, I'm just wondering about the last slide
Yes.
of the fatty acids of C20, C22, etc., that you can separate it this way.
Right.
To the best of my knowledge, this has not done, but has not been done by any other methods, right?
It is being done by other methods, but you wind up going, it's not done on the side of it, it's done on chromatography.
Yes.
Yeah, it's done with chromatography. So, I mean, that is typically the way they are separated now. And this is the basis here is on the basis of solubility, as we see. But it is the separation typically is done with chromatography. Yeah.
في أي أسئلة لحضراتكم؟ شكرا. في أي أسئلة لحضراتكم ثاني؟
They are tired now.
اوكي، ما فيش اي اسئله. بشكر حضراتكم جميعا لتشريفكم، وارجو ان يكون الندوه كانت على مستوى المأمول من حضراتكم متوقعينه. ولو في اي ملاحظات يعني يسعدنا ان احنا نسمعها من حضراتكم، يكون الندوات اللي جايه افضل وافضل باذن الله. في النهايه بشكر الدكتور مختار بيش ممثلنا من شركه باكو، بشكر المهندس حلمي شركة PSI. Thank you, Dr. Rolf, for the very interesting lecture. شكرا لكم جميعا. إن شاء الله نشوفكم في مؤتمرات وندوات علمية أخرى بإذن الله. أهلا بكم طبعا، وأهلا بكم دائما في جامعة المستقبل، وإحنا سعداء جدا. Thank you very much.
كله جاهز؟ ثواني عشان الفيديو كمان بيصور.
Please slowly.
تمام.
بسم الله الرحمن الرحيم. النهارده 21 فبراير عملنا سيمينار ندوة مبسطة في ضيافة الدكتور أسامة عن استخدام السوبر كريتيكال فلويدز في الاكستراكشن بتاع الهيربال ميديسينز. الفايدة بتاع الندوة إن إحنا بنحافظ على البيئة بعدم استخدام السولفنتس التانية، بنوفر ثمن السولفنتس في الكوست، بنقلل في الكوست بتاع الاكستراكشن، بنقلل في الاريا المطلوبة والمخازن المطلوبة لتخزين السولفنتس وتخزين الاكستراكس، بنحافظ على صحة العاملين في مجال الاستخلاص. والأهم من ده الخلاصة اللي بناخدها خلاصة بيور خالية تماما من سولفنت ريزيديو، وده أهم حاجة في عملية تصنيع الدواء. فالفكرة كلها إدخال تكنولوجي جديد عشان نحافظ على صحة المرضى، نحافظ على البيئة، نوفر للاقتصاد القومي التكاليف التانية بتاعة الاكستراكشن باستخدام السولفنتس في عملية الاكستراكشن. ده الملخص اللي نقدر نقوله عن هذه الندوة. والحمد لله ده كان من خلال مشروع عملناه مع وزارة البحث العلمي بالمشاركة مع جامعة فيوتشر وشركة ميباكو والاستف اللي هو البحث العلمي كان عليه التمويل، واحنا قمنا بالعمل كله. والحمد لله النهارده الواحد يفخر ويقول بثقة كاملة ان احنا كوننا فريق عمل يستطيع تشغيل السوبر كريتيكال فلويد اكستراكشن سيستمز سواء في الاناليتيكال او اللاب سكيل او في البايلوت سكيل. واحنا بنخطط حاليا وعاملين انفستمنت ان احنا نشتري اندستريال سكيل يصل الاكستراكشن فيسل بتاعه الى 1 طن. احنا حاليا بنشتغل على 20 لتر اللي هو البايلوت سكيل، هنشتغل ان شاء الله على 1 طن بحيث نوفر الخلاصات المطلوبة للصناعات الدوائية، نقلل عملية الاستيراد، نزود العملة الصعبة للبلد بدل ما نستورد بيها من الخارج نوفرها للبلد. وده الهدف الرئيسي للشغل بتاع النهارده.